Hi everyone, my name is Connor Goggins and I'm a software engineer on the Sagemaker debugger team in AWS AI. So today I'll be walking you through an overview of what model pruning is, explaining why it's becoming increasingly important for the training, inference, and deployment of modern machine learning models. And then Natalie will show you her demo of iterative model pruning using Sagemaker debugger that illustrates how our team's product can be applied to effectively reduce the size of models, decreasing deployment costs and inference times while preserving accuracy. So let's get started. First, let's consider the current state of the art in computer vision and natural language processing. The most sophisticated image classification models contain at least tens of millions of trainable parameters, and the best language models contain hundreds of billions or even trillions of parameters. Note that the y-axis of this chart is on a logarithmic scale. If it were on a linear scale, none of the pre-2020 models would be visible at all because the size of optimal models has increased so dramatically in the past year and a half. Consequently, training these massive models is highly computationally intensive, making it a significantly expensive process. Furthermore, the sheer size of modern machine learning models often makes deploying to edge devices and achieving fast inference times particularly challenging. So with that in mind, researchers are starting to look into ways of making models smaller in order to reduce training costs, deployment costs, and inference times. The three most popular techniques for reducing model size are quantization, knowledge distillation, and model pruning. Quantization is the act of converting the data types of model inputs and weights into smaller types with the goal of using less memory and making calculations faster. So for example, you could quantize a network that uses 32-bit floats to one using 8-bit integers. Since one, the 8-bit integers are 4 times smaller than the 32-bit floats, and two, 8-bit integer math is generally simpler and therefore faster than 32-bit float calculations. The reason we, the Sagemaker debugger team, don't focus on this type of model compression is because approximating the parameters using smaller data types sacrifices precision for a compressed representation. And research has shown that there's often a direct relationship between the reduction in model size and a commensurate reduction in accuracy using this technique. The second popular technique is knowledge distillation, which involves training a much smaller student model to approximate the predictions of a much larger trained model. Even though this strategy has seen some success in applications to large language models like BERT, we don't focus on this technique because it still requires training the complex large model in the first place in order to gain the refined representation. And although inference might be cheaper, the training process becomes more expensive because now you're training two separate models instead of just one. And that brings us to the third and final model compression technique, model pruning. So what is model pruning? Model pruning at the highest level of abstraction is the act of identifying and removing redundant parameters in a machine learning model, which results in a smaller model size, faster training times, and faster inference times. We're focused on a variant of this called iterative pruning, which involves regularly removing weights during the training process. The key revelation behind the feasibility of model pruning is that all of the millions of weights in state-of-the-art machine learning models are not equally important during training. The reality is that certain parameters in the models are critical to obtaining accurate predictions, while others are significantly less relevant and can be pruned or removed. So what you're seeing in this visualization on this slide is a heat map of activations for a small image classification model trained for classification on the MNIST dataset. The yellow and pink colors indicate high activations, while the blue shades indicate lower or non-existent activations of neurons. And you can see that many of the parameters in this model are blue, indicating that they aren't being effectively leveraged for classification purposes and can be pruned to achieve a smaller model size with faster training and inference times while retaining accuracy. There are several different types of iterative model pruning. One is non-structured weight pruning, which analyzes the model, determines the lowest and therefore least relevant individual weights, and then removes them from the model graph, resulting in fewer connections overall. Another technique, which we'll see Natalie apply in her demo shortly and which is particularly relevant to CV models, is structured pruning, which involves removing groups of weight connections, such as entire filters and channels. In this case, the technique is applied to convolutional layers. So those gray boxes on the image of the number 7 are visualizations of filters, which process the input from the section of the image that they include into a feature map. And in practice, there will be many filters applied to this input as the kernel convolves over the input. We can identify the filter that has the least significance. Let's say it's this golden filter here, and remove it from the model entirely. So in one step, we've removed 1 times kernel width times kernel height parameters. So a much bigger reduction than the removal of individual connections at a time, as we saw in the previous slide. And we have a variety of techniques for determining the significance of filters, including finding the minimum weight out of all of the filter's weights, finding the average activation, and finally finding the product of the activation output and its corresponding gradient in the cost function. And this final strategy is what Natalie will use in the demo. So given the high performance and exciting applications of large language models, I also want to discuss strategies for pruning sequence models. As you might guess, the architecture of these transformers is completely different from the convolutional neural network architecture of the model that we just applied structured pruning to. And consequently, a novel approach to structured pruning is necessary. If we look at BERT as a representative example of massively large language models, one of the primary innovations of the model architecture is a concept called attention. The attention mechanism allows the model to alter the weights of input features based on their importance to the unsupervised learning objective used during training. And it also supports establishing relationships between input features. At a high level, the way this is done is by processing embeddings for each element in the input sequence. So this would be a word token or a subword token in a sentence or many sequential sentences provided to the model. Then calculating a matrix of attention weights to determine the relevance of each element in the sequence to each of the other elements. And finally, generating a new sequence of embeddings by calculating a weighted average of the original embeddings using the attention weights. In doing so, the model produces a sequence of context-sensitive embeddings that accurately preserve not only the meaning of the individual words, but also their meaning within the context of the overall sentence. The BERT model includes many modules for evaluating attention, which are independently applied to the same input sequences or stacked on top of other attention layers to learn a wider variety of contextual relationships. And these attention modules are called heads. Now, while attention as a whole is critical to the functionality of BERT, many heads in the model can actually be removed or pruned without damaging the overall performance. So that leaves us with the task of identifying the least important heads in the model to prune. As with filters in the structured pruning example for the computer vision model, there are several ways of determining the significance of heads in a BERT model for subsequent pruning. This includes finding the minimum, maximum, or average weight in each head, calculating the confidence of each head, which basically involves taking the average of the maximum attention weights for each head applied to a set of sample sequences, and then also layer-wise relevance propagation, which essentially allows us to measure the intra-model relevance of individual neurons. Okay, so now Natalie will walk through her notebook POC on iterative structured pruning for a ResNet model using Sagemaker Training Job.
So in this demo, I'm going to show you how you can run iterative model pruning on Amazon Sagemaker. Before we jump into the notebook, let me walk first through the workflow. To run the iterative model pruning workflow, we will use Sagemaker Debugger in combination with Sagemaker Experiment. When you run your Sagemaker training, then it's running inside a training container. We will use Sagemaker Debugger to automatically emit tensors such as weights from our training job. And then, once the training has finished, we will fetch the data from the Amazon S3 bucket. We will use the tensors to compute a filter rank for our convolutional neural network. Once we have the filter rank, we will prune the lower ranking filters and then define a new and pruned model definition with the latest weights. We will then start a new training job. We do that in an iterative way, and in each iteration we remove a certain percentage of the weights of the model, so our model becomes smaller and smaller. And in each iteration we let the model fine-tune for a couple of epochs. We do that because every time you remove weights, you kind of damage the model and it loses accuracy. By allowing the model to fine-tune, it can regain accuracy. We track the different training jobs via Sagemaker experiments. We create an experiment, and each training job in this experiment will be represented via a trial. And then we can use Sagemaker Studio to also visualize some key metrics of our pruning experiment. Before I go to the notebook, let me just give a very high-level overview of what Sagemaker Debugger is. Amazon Sagemaker Debugger is a feature that allows you to automatically capture tensors from your model training. We have modified the Sagemaker default DLC containers in a way that you as a user do not have to modify anything in your training script nor in your model. You simply specify the tensors you want to have emitted, and Debugger will take care of the rest. Debugger also supports a few other features that I would like to highlight. It supports real-time profiling, so you can use Debugger to find computational performance issues in your training pipeline, as well as monitor utilization and profile GPU kernels. Debugger also provides automatic error detection. It comes with a whole set of built-in rules that you can use to find model quality issues, such as over and underfitting, as well as performance bottlenecks. And you can use Sagemaker Debugger for real-time monitoring and visualization. In the demo, we will leverage the SMDebug API to fetch, query, and filter the data. SMDebug is Debugger's open source library that provides you all the basic functionalities you need to read and analyze the data. Let's take a brief look. So in our use case, we want to capture the weights and a few other tensors that we will use to compute filter ranks. On Amazon SageMaker, I simply have to specify now a debugger hook configuration, and Debugger will provide default collections for weights that I'm selecting here. As a user, I can also define my own custom collection, and that's what I'm doing in the second collection. I specify here now a collection ReLU, and I just need to specify a regular expression of the tensor names I want to have included in this collection. Once the Sagemaker training job is running, I can now use the SMDebug API to access and filter the data. I use here now the create trial function, where I pass in the S3 location of the tensors that have been recorded. Once I have the trial object, I can start iterating over the data. I get here now with trial.steps all the different iterations that have been recorded throughout the training. By default, Debugger will capture every 500 iterations. With trial.tensor, you will be able to access the tensors itself. You have to pass in the tensor name, and then with .value and a specific step number, you will basically retrieve the tensor as a NumPy array. So you can use tools such as Matplotlib, scikit, and SciPy to visualize and analyze the data. And you can do that in real time while the training is still in progress. So in this case, with just a few lines of code, I create a real-time visualization of my activation outputs, in this case for my first convolutional layer. Okay, so let's go to the demo. So in this notebook, I'm now going to show you how I use Sagemaker Debugger in combination with Sagemaker experiments to run the iterative model pruning. The first step that I'm going to do is I'm going to use a pre-trained ResNet model from the PyTorch model zoo In my case, I'm using a ResNet 18 model. And first, let's take a look on the model itself. Here I'm seeing the architecture of the model. ResNet models consist of a number of basic blocks where each of them consists of convolutional layers followed by batch norm and relo activation. There are different types of ResNet models, so here I'm using the smallest one, ResNet 18. But we could also use larger ResNet models. The ResNet model is trained on a dataset that has 1000 image classes. So the first step is I have to adjust the final layer of my model. I'm going to train this model on a new dataset, the Caltech 101 dataset. And because this only has 101 classes, I need to adjust the final layer of my model. The next step is that I simply save the model definition together with the weights in a separate output file. Now I would like to track all my pruning iteration in a Sagemaker experiment. And in order to do that, I use now the SM experiments library, and I create an experiment where I simply have to pass in a name for my experiments. So once you have done that, what you can do is you can now go to the experiment view in Sagemaker Studio. You can select it here in the side panel. You select here experiments and trials, and then you will see the created experiment here in the list. So now let's look at the iterative model pruning step by step. As I mentioned, I would like to track my training jobs with Sagemaker experiment. So in each iteration, I will create a new trial object. I use the experiment's trial function, pass in the name of the experiment, and then I will use that trial later on when I start my Sagemaker training job, so that Sagemaker can associate the training job with the specific trial and experiment. Next, I specify the debugger hook configuration. In my case, I would like to capture the weights, as well as the running mean and variance from the batch norm layers, and I capture also the activation outputs because I'm going to use this information to compute later on the filter ranks. And I'm saving this data every 100 iterations. Now I'm ready to start my Sagemaker training job. In my case, I'm training a PyTorch model, so I use Sagemaker PyTorch Estimator API. I train the model on a P32X large instance. My training and the fine-tuning of the model is defined in the train.py file. And the only thing I have to do now is I have to indicate the debugger hook configuration. Before I start the training, I define the experiment configuration. This is a dictionary where I pass in the experiment name as well as the name of the trial object that I created. And when I call estimator fit, this will now start the Sagemaker training job. I pass in the experiment configuration that I defined that allows Sagemaker to associate the training job with my given experiment and trial. And when I started training job, Sagemaker debugger will now ensure that the tensors that I have specified here in my debugger hook config will now automatically be emitted in real time. Once the training job has finished, I will now fetch the gradients and all the other tensors. So first, I create a trial object, and I can use the estimator object to get the path to where the data is located. And now I will use debugger to fetch the tensors and compute a filter rank. Let's first just take a brief look on what a convolutional layer is and a filter and kernel. So when you define a convolutional layer in PyTorch, Then you have to specify the number of input channels, the number of output channels, as well as a kernel size. A filter is a set of kernels. In our case, it has a size of 5 and 5. Then, in my case, I'm running it over the MNIST digit dataset. And this is grayscale image, which only has one channel. That's why I specify here my input channel as 1. And then each filter will create a feature map. And usually you're not just having one filter and one feature map, but you have multiple filters, so they create multiple feature maps, in my case 64. And I want to identify now the filters that are the smallest one, and I will remove the entire filter and as such the entire feature map. So let's take a look on how we can compute those ranks. I use now the SMDebug API to access my activation outputs as well as the gradients, and I do that for all the steps that have been recorded throughout the entire training phase. I then build a product of activation output and gradient. I average that over the different dimensions. I normalize the filter, so I have here a helper function, and then I sort the filters across the entire model. So I have here another helper function that will now return me a list of the 100 smallest filters. Let's take a look. The list tells me that the first entry is basically the smallest filter. It tells me that the 272nd filter in my fourth layer in the model had the smallest value. And with this list, I can now start going through my model and remove the filters that are too small. I have created a function that basically what it does, it will now analyze the model and identify the layers and the filters that can be pruned. The function will now give me some output like the following. It tells me, for instance, that in the first layer of my Resonate 18 model, it removed the size of the filters from 64 to 63. So once I have the new model definition with the latest weights, that's what this function is going to return me. I'm just saving this model definition and I can start the next training. The next training will now pick up the latest pruned model and fine-tune it for a couple of epochs. So this is now the iterative model pruning step by step. So we went through all the different steps that I explained before in the presentation. And now we can just take all these code pieces together and run it in like one big loop. Let's take a look. So here I'm running now 10 pruning iterations. So in each iteration I'm removing the 100 smallest filters, so my model becomes smaller and smaller. As discussed before, for each iteration I want to have a new trial object in the experiment. I then start the training, and once the training has finished, I will now compute the filter ranks, normalize the filters, and then remove the smallest filters, save the new model definition, and then I can go to the next iteration and everything starts again. So we can now go to Sagemaker experiment view in Studio to track the experiment. So when you open the experiment that you created, you will see all the different executions. So each trial corresponds to one training job. You can then open it in the experiment view. Let's take a look. Here we see now each row is a different training job. And for each of these training jobs, I also saved some additional metrics, such as the accuracy, the validation accuracy, as well as the number of parameters. So the non-pruned model started with around 11 million parameters, and I run here roughly 12 pruning iterations. After the 12th pruning iteration, I only had 75,000 parameters left in the model. When I look at the validation accuracy, I can see that it's roughly the same for many iterations, but in the end, the accuracy significantly drops. So if I go below like 2 million parameters, then the model becomes really bad. And that happens because it has basically a too low capacity. We can now also create visualizations. So here I visualize the number of parameters on the x-axis versus the validation accuracy. And we see that my accuracy is always above 80% until my model only has 2 million parameters. Then it starts dropping. So I run this iterative model pruning workflow on different kind of models. And the animation that we can see here is shows the different pruning iterations of an AlexNet model. So what we see here is the model definition, and we see here the number of parameters as they become less and less in each iteration. And this animation actually shows that most of the weights are pruned in the last layer of the models. And that's kind of very typical because the early layers in your model, they learn very important features, while the last layers in the model typically learn some redundant features. So you would often observe that during pruning, the last layers will be pruned more often. Thanks a lot for attending our session.